Alright, welcome to our third video. We're looking at how molecules get made today. So we're going to look at the three main different types of bonds that we see in molecules. So let's get into it. Alright, so most elements bond with each other in certain ways. Now, there is an exception to this. If an element or an atom of a certain element has a full outer shell, they're not going to form bonds. Hopefully you remember the group that do this. We say they're inert and that they don't bond with anything, and they've got a special name, and that name is noble gases. On the other hand, all other elements actually are going to react, and they're going to form one of three types of bonds. Now, if you have a metal and a non-metal, they bond together and they form what we call ionic bonds. And the reason for this is that because to form that bond, they actually need to form ions. And so because they form ions, they have an ionic bond. If, on the other hand, you have two non-metals joining together, you get what's called a covalent bond. And this is because the co there means like to share, and valent is referencing valence electrons. So covalent bonds are those that are formed where atoms are sharing their valence electrons. Finally, if you have metal atoms, we get metallic bonds. Hopefully that's pretty obvious why they're called metallic bonds. So let's get into that into more detail. So like I was saying, with ionic bonding, ionic bonds are those that form between a metal ion and a non-metal ion. So because we've got ions, we have ionic bonds. Now, we notice a certain pattern with, just jump back there. With our metals, they always lose electrons. So metals always lose electrons in ionic bonds, and because they're losing a negatively charged electron, they're going to form a positively charged metal ion. On the other hand, our non-metal atoms always gain electrons, and because they're gaining that negative electron, they're going to form a negatively charged non-metal ion. So we have this positive metal ion and a negative non-metal ion, and those opposite charges attract each other and they bond together. And we could simply say that the metal and the non-metal bond together because the metal gives up its electrons to the non-metal. Got a little bit of a diagram here. You can see we've got one atom here giving away an electron to another atom. That's pretty much what happens in these kinds of bonds. Now, just going into this in more detail, remember that when atoms either lose or gain electrons, they become ions. We have a couple of specific names for our two different types of ions, depending on whether or not it's a positive or negative charge that they have. So if ions lose an electron and if an atom loses an electron and forms a positively charged ion, like our metals do, this is known as a cation. One fun way to remember that this is cats have pores and cations are positive. So I don't know if that helps you or not, but that's one way you can remember what cations are. On the other hand, our non-metals, they gain their electrons and they form a negative ion, and we call this an anion. So anions are ions with negative charge, and they're formed by non-metals in ionic bonding, the non-metals that have gained electrons. Alrighty, what would the following form? Dun, dun, dun. We've got magnesium, sodium, an OH group, which we call hydroxide, chlorine, oxygen, and an SO4 group that we call sulfate. So pause the video, have a bit of a think, look it up if you need to, and see if you can work out the answers. Alrighty, how did you go? Alright, let's go through this. So it's not too difficult. If you remember whether or not it's a metal or a non-metal, that's going to give you an indication of whether or not it forms the cation, which is positive, or the anion, which is negative. So I'm going to go through and I'm going to put a plus for the cations and a minus for the anions. So magnesium is what we're starting with, and magnesium is a metal, so it's going to form a plus, a positive cation. Moving to sodium, sodium's also metal, so it's also going to form a cation. Now, our hydroxide group, the OH there, both of those are non-metals, and they're behaving in this instance as a single thing, as a single unit, a single atom. They're two atoms joined together, but they're behaving like they're one. And so they're both non-metals, so this is going to be a negative. All right, then we have chlorine, another non-metal, so another negative. Oxygen is a non-metal, so it also is a negative. And sulfate there, again, we've got 5 atoms actually here all joined together, but again, they're behaving like one thing. And these are, again, our non-metals, so again, they're behaving like a negative, or they are a negative ion. So you should have gotten 2 cations and 4 anions there. Alrighty, so we actually have some tables here where we can look at different types of ions. So this table is just positive ions, so just cations, and you can see here we've got our first column are all ions or all cations that have a +1 charge. So this means that they lose 1 electron. So you've got hydrogen, potassium, silver, sodium, and what we call ammonium. Ammonium being an NH4 group. Now I know we were saying that our metals form cations, but you've probably noticed that hydrogen and ammonium are not 2 that we would think of as metals. Nitrogen is a non-metal, and hydrogen tends to be thought of and treated as a non-metal. Well, hydrogen's the odd one here, and it's the reason that this is in the cation group. Hydrogen, because it's only got 1 electron, it's not held on very tightly. Even though traditionally we're not putting it into that metal category, behaves as a metal and forms a cation in this instance. And that's why the ammonium's there as well, because even though it's got nitrogen, it's got a lot of hydrogen, and they're the ones dictating the charge on this. All right, then we've got our +2 column in the middle here. We've got calcium, copper, iron, lead, magnesium, and zinc. Now you might have noticed both copper and iron have the number 2 in brackets after them. That's 2 in Roman numerals, so it's II. And there's a really good reason for this, because if you look in our third column, we've got aluminium, but then we've got iron again. So we actually see iron popping up 2 times, 1 here and 1 here. And the reason for this is iron is in a bit of an interesting position. It actually can lose different amounts of electrons. It might lose 2, in which case it's going to be in the +2 category, but it might also just as easily lose 3, in which case it's going to be in the +3 category. So we have to show it twice because it can form 2 different types of ions. And the way we indicate to someone who might be reading what the sample that we're talking about is, or something like that, is we use Roman numerals after the first word to indicate which ion we're talking about. Are we talking about ion 2, where it loses 2 electrons, or are we talking about ion 3, where it loses 3 electrons? So that's what we use those Roman numerals for. Alrighty, here is our table with our anions, our negatively charged ions. So again, we've got our first column. These are all atoms that have gained 1 electron, so they have a -1 charge. So we've got bromide, chloride, hydrogen carbonate, hydroxide, iodide, and nitrate. Now, a few things to note. First of all, we have bromine, chlorine, and iodine atoms that have all gained an electron, and their names have changed. And you'll notice this in other places in the table as well, that when you have a non-metal that gains an electron, becomes a negative ion, the end of the word tends to change to IDE. So instead of bromine, we have bromide. Instead of chlorine, we have chloride. Instead of iodine, we have iodide. If you look in the 2 column, instead of oxygen, you have oxide. Instead of sulfur, you have sulphide. And in the 3 column, instead of nitrate, you have nitride. So this is a pretty consistent pattern. With our other ones in that first group, you'll probably notice that we've got 3 that are what we call polyatomic ions, and we'll touch on this on the next slide, but it simply means it's an ion that has more than 1 atom in it. So you've got HCO3, OH, and NO3 here, and that's in the -1 column. And basically this is more than 1 atom that's joined together in its own little group already, and they just go around pretending that they're like a normal ion like everything else, and they're just like they're 1 atom instead of acting like a whole group. So we have to treat them when we work with them as though that they are just like 1 ion or 1 atom sort of thing. We have more of them in the -2 column. We've got carbonate and we've got sulfate. You've also got oxide and sulphide there, but those are just normal ions that are made up of 1 atom originally. In our -3 column, we have phosphate, which is PO4, and then you also have nitride. So phosphate is our polyatomic ion there. So this is what I was talking about. If you have an ion that's made up of just 1 atom, that's what we call a monatomic ion. Mon at the start there means one, and atomic means, how many atoms there are. On the other hand, if you have an ion that's made up of more than one atom, that's a polyatomic, because as we already know, poly means many, and again, atomic just means atoms. So those polyatomic ions, they're charged particles, they're made up of more than one atom. You can see here some examples, so sulfate, hydroxide, ammonium, which is our positive one. The negative ions are much more common in terms of having this and what we'll be working with. If you have a molecule that has, you've got your positive ion there, but it's attached to a polyatomic anion, something like hydroxide, if you've got more than one of those polyatomic ions, we actually use brackets to indicate this. And that way we can communicate to people that we're actually not just talking about, 2 oxygen and 2 hydrogen, we're actually talking about 2 what we call OH groups. And that's important because that gives that molecule certain properties, and we would expect it to behave in a certain way and be structured in a certain way. So it's part of communicating some structure. That's why we include the brackets. All right. So what I want you to do now is write out the chemical formula for the following polyatomic ions. So you've got sulfate, hydroxide, and carbonate. Feel free to pause the video. You can go back and look at the previous tables and try and find your answers there. So pop the video or pause the video and go and do that now. Alrighty, how did you go? Well, let's go through this. So sulfate should be SO4. If you include the charge, it is 2-. Hydroxide would be OH-, and carbonate would be CO3, 2-. So there we go with our answers. Alrighty, so let's move on and let's talk about iron again. So as I was saying earlier, some metals can form different ions with different charges. The main one we looked at before was iron being able to form Fe2+ and Fe3+. Copper was also in our table, but we only put in copper 2, but you can have copper 3. And these are not the only 2 metals that do this. Other ones are able to do it as well. Iron happens to be a particularly common one, and so does copper. Like I was saying earlier, when we write this as a word, you need to use Roman numerals to show what form it's in. So if I was talking about copper sulfate, it would be important for me to say copper 2 sulfate so that whoever's reading it or whoever I'm talking to knows what kind I'm talking about, because it's going to have different properties and behave differently to something like copper 3 sulfate. It's going to have a completely different structure. And so if I say copper 2 sulfate, that 2 means that it's 2+. If I'd said copper 3, that would be Cu3+. Okay, so the name does mean something quite important. Alrighty, let's get started talking about how we actually form ionic compounds. We've sort of touched on it briefly, but I want to get into it in more detail. Now, ionic compounds form when cations are electrostatically attracted to anions through ionic bonding. What this really means is that the positive charge on the cation is attracted to the negative charge on the anion. So those 2 opposite charges attract each other, they pull them together, and we end up with an ionic bond. And these ionic bonds can be really strong and really stable. For example, table salt is actually something called sodium chloride. A lot of you might already know that, but basically it's a really stable compound because that bond between the sodium and the chlorine is so strong, and it happens to be an ionic bond. So what happens is, what are these atoms or these ions trying to do? Well, they're trying to be nice and stable, and essentially they're aiming for electrical neutrality. And all I mean by that is that they want to bond together and end up as a molecule that doesn't have an electric charge. So when we're looking at working out how these molecules form, we're trying to balance the positive and negative charge. So we've got magnesium chloride as an example here. Magnesium is Mg2+, and chlorine is Cl-. So magnesium has 2 positive charges, and chlorine has 1 negative charge. Now, if you put just one of each together, you're going to have more positive charges. So what you actually need to do is you need to have 2 chlorines for every 1 magnesium. And what that's going to do is that's going to mean you've got 2 negative charges and 2 positive charges, and they'll cancel each other out, and you'll get an overall charge of 0. And you can see in the diagram here to the right, that's what's happening. We have 2 chlorines and 1 magnesium. Alrighty. Some properties of ionic molecules and compounds. So as we've already said, they're made up of positive and negative ions. And the reason I keep going over this is it's really important for you to understand that, because there are times when you can break those bonds and they're going to break back into these ions. All right, they also tend to be normally solid at room temperature. Their melting points tend to be on the high side of things, and they tend to dissolve in water and form what we call aqueous solutions. An aqueous solution, if you've not heard of it before, is simply a solution where something has been dissolved in water. A lot of the time in science, particularly in chemistry, we're going to be working with aqueous solutions. So when we're writing out our chemical equations, we put that as an AQ, not an L. So if you had a solution of sodium chloride, you actually write AQ after that, not L, because L would be like if you'd taken a bunch of sodium chloride and you'd melted it and you heated it up really, really high till it was molten, and then it became a liquid. If you put it into water, that's actually an aqueous solution. So it's good to be clear on the difference between those two. With ionic compounds, when you do make an aqueous solution, normally you're going to find that those solutions conduct electricity, and that's because the ions do what we call dissociating in that solution. So they actually do sort of separate and they're free to move, and electricity needs charged particles that are able to move to be conducted. So now we have this solution where we have these differently charged particles that can move. So that's why they tend to conduct electricity. Now, I want to start getting into talking about how can you actually take two different ions, take a positive ion and a negative ion, and work out what molecule they're going to form. Well, there is actually a really handy trick that we're going to get to in a moment. So you need to remember that in ionic bonding, elements are forming a compound by donating or accepting electrons, and it's going to occur between a cation and an anion, or a metal and a non-metal, I should say. The net charge overall in that ionic compound is going to be 0. So the sum of the positive charges equals the sum of the negative charges. So however many positive charges you have is going to be equal in size to the negative charges. And we've got a little diagram down here showing something called the crossover method. In fact, to get into the crossover method in more detail, we're going to watch a little video.
The crossover method is a shortcut way of writing formulas for ionic compounds if you know the charges on the ions in the compound. We'll go over a few examples. In example A, we're asked to write the formula for magnesium chloride. Looking at magnesium on the ion table, or periodic table, we see it's Mg with a charge of 2+. And chloride is Cl with a charge of minus or -1. We start the formula by writing down the symbols, Mg and Cl. Now we take the 2 from the charge on the magnesium, cross over, and write it next to the chlorine. Now we could take the 1 from the charge on the chloride, cross it over, and write it next to the magnesium, but we don't use the subscript 1 in a formula, so we don't need to write anything. So the formula has 1 Mg and 2 Cls. So we'll compact it and write the final formula for magnesium chloride as MgCl2. We'll check the charges to verify that this formula is correct. We have 1 Mg2+ ion and 2 Cl- ions. So the total charge is +2 plus 2 times -1, or +2 plus -2, which is equal to 0. So the formula MgCl2 is correct. Example B asks us to write the formula for calcium oxide. We look up calcium and it's Ca with a charge of +2, and oxide is O with a charge of -2. We start the formula by writing down the symbols Ca and O. The charge on calcium is +2, so we cross over and write a 2 next to oxygen in the formula. The charge on oxide is -2, so we cross over and write a 2 next to calcium in the formula. Notice we always drop the negative when we write subscripts. Now we have the formula Ca2O2. But you can see that both of the subscripts in this formula are divisible by 2. So we simplify and divide both of these by 2 and get 1s. We do not keep the subscript 1 in a formula, so we remove the 1s, leaving us with the formula CaO, which we'll compact and write as the final formula for calcium oxide. Checking charges, we have 1 Ca2+ ion and 1 O2- ion. So the total charge is +2 plus -2, which is equal to 0. So this formula is correct. Question C asks us to write the formula for chromium 3 sulphide. The chromium 3 ion is Cr3+, and the sulphide ion is S2-. We start the formula with the symbols Cr and S. We take the 3 from the charge on the chromium, cross over, and write 3 next to sulfur in the formula. And we take the 2 from the 2- charge on the sulphide ion, cross over, and write 2 next to chromium in the formula. There is no number other than 1 that will divide into 2 and 3, so this formula cannot be simplified. So the final formula for chromium 3 sulphide is Cr2S3. Checking charges, we have 2 Cr3+ ions and 3 S2- ions. So the total charge is 2 times +3 plus 3 times -2, or +6 plus -6, which is equal to 0, so this formula is correct. Question D asks us to write the formula for palladium 4 oxide. Palladium 4 is Pd with a charge of 4+, and oxide is O with a 2- charge. We start the formula with the symbols Pd and O. We take the 4 from the charge on palladium, cross over, and write 4 next to oxygen in the formula. We take the 2 from the charge on the oxide ion, cross over, and write 2 next to palladium in the formula. Now we have the formula Pd2O4. But we see that both of the subscripts 2 and 4 are divisible by 2. So we simplify by dividing the 2 and the 4 both by 2, giving us 1 and 2. We remove the subscript 1, leaving us with the formula PdO2, which will compact and state as the final formula for palladium 4 oxide. Checking charges, we have 1 Pd4+ ion and 2 O2- ions. So the total charge is +4 plus 2 times -2, or +4 plus -4, which is equal to 0. So PdO2 is the correct formula for palladium 4 oxide.
Alrighty, how did you go with that video? Hopefully it made sense. What I want you to do now is actually take what you've just learnt, pause this video, and I want you to go through the 4 molecules there: sodium oxide, magnesium chloride, aluminium sulfide, and lithium fluoride. You can use the 2 tables earlier in these notes to help you work out how to do these ionic molecules. Remember, you're going to need to work out what each ion is, and then you can use the crossover method for it. A heads up, lithium fluoride isn't in those tables, neither lithium nor fluoride. You're going to have to go to the periodic table and work out what ions they would form. Don't worry, they're both really easy. So pause the video now and go and give that a go. Alrighty, so going to go through these now. We'll start with sodium oxide. So write this here. Sodium oxide. Sodium you should have found is Na+. Oxide is O2-. So what do we do with this? Well, if we're using the crossover method, then what you need to do is you need to take this, cross it down over to here, take this, cross it down over to here, and that's going to give us Na2- down here and O+. Now we've got to go and do a couple more steps. So the first thing we need to do is get rid of our charge symbols. So now we've done that, we're then going to look at our numbers. Now the plus was there by itself because it represented 1+, and we just don't bother writing the 1 in. So when we get rid of it, we don't need to replace it with a 1, but just remember that's what is implied, that the O is there and there's 1 of them. Now what we want to think about is our bottom numbers. We've got a 2 and a 1, and those are as simple as things are going to get. We can't make them any simpler. So we don't need to change them, we don't need to reduce anything down. So we've got Na2O, so we would have A2O. And that would be our molecule. So that's how you get sodium oxide. All right, I'm going to clear this and we're going to do the next one. All right, so the next one we're doing is magnesium chloride. Can't write a D very well there, but it's fine. So magnesium, as you would have found, is Mg2+, and chloride, which comes from chlorine, is Cl-. So again, we're going to do our crossover, this down to here, this over here. That's going to give us Mg minus and Cl2 plus. So if we go through, get rid of our charge symbols like that, again we've got a 1 and a 2, can't get any more simple, so we're going to go MgCl2, and that's what we've got there. Okay, so we're going to get rid of these and we're going to move on to the next one. Okay, so our next one that we're doing is aluminium sulphide. So we're going to go, oh, I can't spell aluminium, aluminium sulphide. All right, aluminium, as you would have gotten from the tables, is Al, and now we got 3 plus. Ooh. Sulphide is S2 minus. So this is interesting. We'll see where this goes and see what we end up with. So we're going to do our crossover method. We take the 3 plus and we bring it over here. We're then going to take our 2 minus and we're going to bring it down over here. I'm going to rewrite this because it's starting to get quite messy, but we've got Al 2 minus and then S3 plus. First things first, let's get rid of those charge symbols. We don't need them. They can go away. Again, we're going to now look at our numbers. We've got a 2 and we've got a 3. Now, there isn't anything you can divide both of them by to make them a simpler whole number, so we're going to leave them as is, and we'll rewrite this nice and neatly, Al2S3. And there you go. That's aluminium sulphide done and dusted. Okay, moving on to our last one. Now, this one was a little bit trickier because you didn't have these in the tables. You had to look them up on the periodic table. But we're doing lithium fluoride. So write this out. Lithium fluoride, F-L-U-O-R-I-D-E. There we go, lithium fluoride. Lithium is Li and it's in group 1, which means it is just a plus, and fluoride comes from fluorine, and fluorine is in group 17 and it is F, and because it's in 17 it is just a minus. So this is what I meant by it's an easy one. We can go through the crossover method. You might have already noticed this is pretty simple what you need to do, but if you're going through the crossover method, you're going to take this here, then you're going to put this here. We're going to get Li minus F plus. We get rid of our charge symbols. It's 1 to 1, so we just rewrite it as LiF, and there we go. And that's it. That's all you need to do for lithium fluoride. Alrighty, so now we're going to jump to the covalent bonding. So we've finished ionic bonding. If you weren't fantastically comfortable there at the end with your ionic compounds and how to do the crossover method, go back and do some study where you're going to go to those tables, grab 2 different things and see if you can work out what it is. And you can go and either check that online or check it with a teacher to see if you've gotten it right, and that will be some really good practice for you. But like I said, we're moving on now to covalent bonding. So covalent bonds are the bonds that form between 2 non-metal atoms. So things happen a bit differently here, because now we're not talking about a non-metal and a metal who have formed ions to join together because the metals giving up their electrons to the non-metals. No, now we're talking about 2 non-metals. So they can't both steal electrons from each other. That's not going to work, so they're going to have to do something different. Now, I mentioned earlier that covalent bonding, the word covalent, is coming from the fact that they're sharing their valence electrons. Co, because it belongs to both of them and they're shared, and valent because it's referencing the valence electrons. So our non-metal atoms are bonding together because they share electrons to give themselves a full set of valence electrons. Remember, the whole goal of all this type of bonding, particularly with ionic and covalent, is they're aiming for that full out of shell. So ionic bonds achieve this by one lot giving up electrons and one lot taking electrons, and that's how ionic bonds go about getting that full outer shell for their atoms. Whereas in covalent bonding, we have 2 nonmetals, and like I said, they can't both take electrons to fill up that shell, but they can share electrons and put them sort of in between the 2 of them to pretend it belongs to both of them, and that way that's how they can get their full out of shell. We've got our 2 little atoms here at dinner sharing electrons, or we can look at our 2 fluorine atoms here, and I think this is a really good example. It's a little bit like a Venn diagram where the 2 electrons sit in that middle, that overlap, because they belong to both of our atoms. So if you look here at our atom, we've got 2 in here, and then what they want is a full outer shell of 8. So since shell 2, you've got 1, 2, 3, 4, 5, and we're going to count this one 6, 7, and 8. Okay, so those 2 electrons belong to this one, but at the same time, if we go to our other guy here, we go around the other way, we've got 1, 2, 3, 4, 5, 6, 7, and 8 as well. So these 2 essentially end up getting counted twice because they belong to both parties. And that's how those covalent bonds work. They put electrons in the middle and they share them. So we've sort of got a few different types of covalent molecules. We've got, first of all, what we call discrete molecular. And so these are generally what your normal covalent compounds are. So something like water or carbon dioxide. And these are basically, they tend not to be too big and they're pretty contained. For those who don't know, this discrete here doesn't mean private or subtle or anything like that. There's actually 2 different ways of spelling discrete. You've got discreet, and this is the one that means private or subtle. Okay, this discrete actually means not continuous. Okay, so there are actually 2 different words, and it's worth you knowing it, particularly if you are doing an advanced maths as well, because that's the sort of word that will come up, and you need to know the correct spelling. There is actually 2 versions of it. Don't worry if you didn't know, a lot of people don't realise that. But moving on, the other kind we've got is what we call monatomic. And this is something where a non-metal exists by itself. And really we're talking about our noble gases. For example, helium. Okay, helium, if it's out floating as a gas, it's just He atoms, all individual atoms by themselves. And if you remember, this is because they're a non-metal, but they've also already got a full outer shell. So they don't need to try and bond with any other atoms to get that full outer shell. They've already got it. Finally, one that's quite common, particularly given, this is what we're talking about when we're talking about oxygen or hydrogen gas or nitrogen gas. These are what we call diatomic. Now, monatomic was mon for 1, and diatomic means 2. So monatomic means 1 atom and diatomic means 2 atoms. And it happens to be of the same non-metal atom. This is really important. If we're not talking about the same ones, then you're actually talking about discrete molecular type of molecule. And like I was saying, these are things like hydrogen, oxygen, and nitrogen gases. That's the kind that are these diatomic molecules. Now, if you want to draw a covalent molecule, there's a few ways of going about it. We're first going to look at what we call electron dot diagrams. And electron dot diagrams are basically all about looking at how many valence electrons. And that's really important to remember, that it's about the valence electrons. Ooh, jumping around there. It's, like I was saying, about those valence electrons. So what you need to do is you need to write the symbol of the atom, and then you're going to draw dots around that to represent just those valence shell electrons. And so if we look on the right, you can see here we've got, for example, hydrogen. Okay, hydrogen happens to just have 1 electron, so it gets 1 dot, and that's because that electron is its only electron, it's its only valence electron. Carbon, okay, we've got a C for carbon. Carbon happens to have 6 electrons. It's got 2 in the first shell, 4 in the second shell. And so it's that 4 we're interested in. And you can see here that there happens to be 4 dots around carbon. If we move on to oxygen, oxygen has 2 electrons in the first shell, 6 in the second. So we're going to put that 6 around the oxygen. And if you go through, you'll see that something like sulfur, even though it's got more electrons than oxygen, remember it's the valence electrons we're interested in, so it's also only got 6 valence electrons. So like oxygen, it's got 6 dots around it. It's really important that you recognize that it is actually the valence shell electrons that we're using the dots to represent, because otherwise you're going to do the wrong thing. All right, so take a moment now, pause the video and go drawing those electron dot diagrams for the following atoms: carbon, oxygen, hydrogen, sulfur, fluorine, nitrogen, and lithium. Just a heads up, sometimes diagrams are also called Lewis diagrams. That's just another name for the same thing. So pause the video and have a go. All right, how did you go? Hopefully you got through it. So let's go through carbon. We've got a C for carbon. Carbon happens to have 4 valence electrons, so it's going to look like that. Oxygen. Oxygen has 6. 1, 2, 3, 4, 5, 6. Hydrogen is our next one. Hydrogen has 1. Nice and easy. Then we're going to do sulfur. Sulfur also has 6. 1, 2, 3, 4, 5, 6. Fluorine, F for fluorine, and fluorine happens to have 7. So 1, 2, 3, 4, 5, 6, 7. Almost through our list here, we've got nitrogen. N for nitrogen. Nitrogen has 5. 1, 2, 3, 4, 5. And finally, lucky last, lithium. Lithium, very similar to hydrogen. Lithium only has 1 valence electron, so it just gets 1 dot. Now, you might be wondering, yeah, but why do I need to know stuff like this? Well, because we can actually take them and we can use them to work out how the bonding works. Because remember, the bonding for our covalent molecules is entirely based off their valence electrons. So what we can do is we can actually use these diagrams to sort of work out how they're going to bond together. Now I'm going to go through this first one for you, and then I want you to pause the video and work out the rest of them. So we're going to start with chlorine, and what we're going to do is we're going to take chlorine, and chlorine happens to have 17 electrons. So it's got 2 in the first shell. It's got 6, sorry, not 6, it's got 2 in the first shell. It's got 8 in the second, so it's 10. And then it's got 7 in its third shell. So it has 7 valence electrons. And that's true chlorines, because this is Cl2. So we've got 1 chlorine with 1, 2, 3, 4, 5, 6, 7 valence electrons, and I'm going to draw another chlorine right next to it, and it's also got 1, 2, 3, 4, 5, 6. I'm going to put the 7th one here, and there's a really good reason for this, because if we look at this, we could talk about this is 1 chlorine, but we can also say that this is 1 chlorine. So we can use those electron dot diagrams to start building our molecules and work out how those electrons are being shared. So I want you to give this a go. Pause the video and try and work it out for water, oxygen, methane, and ammonia. All right, pause the video now. Alrighty, let's go through these. So we'll start with water, H2O. As you might notice, there's a hint there that says place the atom with the most dots in the center. So this one is really helpful for water. We're going to put oxygen in the center. We're going to put a hydrogen here and a hydrogen here. Now, oxygen has 1, 2, 3, 4. I'm going to go 5, 6 electrons, which means it's got space for 2 other ones. Now, each hydrogen has 1, so we're just going to put that there and put this hydrogen's 1 here. And so you can see oxygen has 8 dots around it, and each hydrogen is next to 2 dots. So that is our water molecule done and dusted. So I'll just quickly show that for you. There's your oxygen. There's 1 hydrogen. There's the other hydrogen. All right, oxygen. We're going to go O here and O here. We've got 1, 2, 3, 4. I'm going to do that on each of them. Now remember, each of these has 6. So this oxygen has 1 here, but it's got another one, and so does this one. Now, unlike all our other bonds, this now has 4 electrons between the 2, and that's because the oxygens actually share 4 electrons between them, and so each oxygen takes up this sort of space. And so what we end up with is here, here this is what we call single bond, this is a single bond, this is a single bond, but this is a double bond. Okay, so 2 oxygen atoms actually bond twice between them. They have 2 pairs of electron. Each pair of electron is what we call a bond. So 2 pairs would be 2 bonds. All right, CH4. So we're going to put carbon. It's got the most dots in the middle, and we're going to put 4 hydrogen around it. All right, carbon has 1, 2, 3, 4, and then each hydrogen has 1, 1, 1, and 1. So we have our carbon here in the middle, but then we have our 4 hydrogen around the edges. Okay, now I should add, you don't need to draw these circles that I'm drawing. That's just to show you how those electrons are being shared. You just need to have them without the circles, and the dots is all you need. So let's move on to our last one, NH3. We've got an N, and we're going to do 3 H's, H, H, and H. Nitrogen has 1, 2, 3, 4, 5, and each hydrogen has 1. Pop them there. So this is all you would need to do would be this, but I'm going to show you just with the circles how those electrons belong to all the different atoms. So we've got nitrogen, our hydrogen, another one, and another one. And there you go. Those are our molecules and how they all bond together. Now, this isn't the only way we can draw our covalent molecules. We can actually draw them in what we call structural formula. And this is where we use the letters and sticks to draw our molecules. It's actually a pretty common way, and you've probably seen molecules drawn like this before. Now, you need to remember what I was saying about the bonds. One bond is one pair of electrons. Two bonds would be two pairs of electrons. Three bonds would be three pairs of electrons. And so you represent this with a line for each bond. So covalent compounds can also be drawn using structural formula, and a line is used to represent one covalent bond. So one covalent bond is a single bond and it's got one line. Two covalent bonds is a double bond and it has two lines. Three covalent bonds is a triple bond and it has three lines. So you need to remember though that each line represents two shared electrons. So this is two electrons, this is two electrons, and this is two electrons. And the same for the ones around here. Sort of a summary of this, so you can see here. So we've got the name and formula on the left of a bunch of different compounds. It then looks at what the atoms are in terms of their dot diagrams, then how they form compounds. And this is really helpful because you've actually got different colors to show where all those electrons are coming from. Then in our orange column, it's looking at the structural formula. So you can see there chlorine has a single bond. It's just sharing one pair of electrons, so it's just got one line. Hydrochloric acid, again, is sharing one pair of electrons, so it just has one line. Our oxygen, remember, that had two pairs of electrons between them, so they've got two lines because that's a double bond. Nitrogen gas is really interesting. It actually shares three pairs of electrons between the two nitrogens. So that's a triple bond, and it's got three lines to represent that. Then we've got a water and a carbon dioxide down there, and on the right in the blue column is an explanation as to why they've bonded this way. So you can pause the video and have a read through that if you'd like. We're also going to look at how we name covalent molecules because there is a specific technique. They're named according to the following rules. First of all, whatever that first element is, you just use its normal name. If you have one of that atom, you just write that as is. For example, if you've got carbon dioxide, it's just one carbon, so we just say carbon. But if you have more than one of it, you need to put what we call a prefix at the start to indicate that there is more than one of it. So if I had a molecule that was C3 something something something, then I would have to say dicarbon. Okay, because I have more than one of those. Okay, and I can look down the bottom here and I can see mono is 1, di is 2, tri is 3, 4 is tetra, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, and dec is 10. They do go higher, but those are the only ones we're going to cover in this lesson. So that's what you do for the first element. Then you turn and you look at your second element and you work out what is that. And then you need to change the end of it to IDE. Now, that should seem familiar. Why? Because this is what happened with our ions. When we had oxygen, it became oxide. When we had chlorine, it became chloride. And basically, when it comes to naming, we're just going to name it in the same way. Again, like with the first bit, you need to include a prefix to show how many there are of that atom. The only difference here is if you have one, you put mono at the start. For the first element, if it's 1, you don't need to put anything at the start. For the second element, if you've got 1, you have to put mono at the start to indicate that it's just 1. So you're probably thinking, yeah, but what does this look like? Well, this is what it looks like. So if we take what we would normally call water and we actually want to work out its proper name, we can do this. So we have our first element is hydrogen. So that's what we've got here. And then we're going to look, well, how many have we got? Have we got 1? No, we've actually got 2. So we need to put that prefix, that di, in front of it to indicate that we've got 2. So di, remember, means 2. So dihydrogen means 2 hydrogen. Then we have our second element, that's oxygen. So remember, second element, you have to change the end of the word. So oxygen becomes oxide. Okay, but we also have to indicate how many we have, and we happen to have 1. And so because this is the second element, we actually do have to put mono at the start. We don't get monoxide, we just go and call it monoxide. So we don't have a double O after the N. And so that's what we've got here. And that gives us this lovely name, dihydrogen monoxide. And that's the proper name for water, but obviously we just generally tend to call it water. If you want, there is a website called DHMO, and it's a bit of a spoof website where it goes through all the perils of dihydrogen monoxide, and it makes this compound sound really bad, and it's quite funny when people finally realize that it's actually talking about water. Alrighty, so it's going to be your chance now. I want you to go through the following compounds. You've got CBr4, NCl3, CO, NO2, P2O5. I want you to go through and name them. And then on the slide after this, you can also go through and match the molecule with its correct name. So I'm going to pause the video and I want you to do those 2 slides, go through them, and then I'm going to go through the answers. Alrighty, let's see how you went. So our first one here, we're going to look at our first element. Our first element is carbon, and there's one of them, so we can just write carbon. Next element is bromine, but it's a second element, so we have to change that to bromide, and we happen to have 4 of them, so we're going to say tetra for 4, and bromide. Alright. So that's our first one, it's carbon tetrabromide. Next we've got NCl3. So again, our first one happens to be by itself, so we can just say nitrogen. And then we're going to look at our second one. We've got chlorine as our second element, but remember that's going to have to change to chloride. And we've got 3 of them, so 3 would be tri, and CHLORIDE. Nitrogen trichloride is what we call NCl3. Okay, so carbon is our first one in our third molecule, so we're going to say carbon again. It's nice and easy because we've only got 1 of it, and then again we've only got 1 of our next molecule, and it happens to be oxygen, so that's going to be oxide, but we've got 1, so we say monoxide. Now you've got carbon monoxide, which you've possibly heard of before. So that's actually why it's called carbon monoxide. It's entirely connected to the actual atoms in the molecule. All right, second to last, we have NO2. N is nitrogen. Okay, and O2, it's oxygen. Oxygen becomes oxide, and we've got 2 of them, so it is dioxide. Okay, so we have nitrogen dioxide. All right. Alrighty, our last one is a little bit trickier. So our first one is phosphorus, but we have 2, so we need to represent that, and we're going to say diphosphorus. Our second element is oxygen. Remember, oxygen becomes oxide, and we have 5 of them, so it's going to be pentoxide. Okay, and that's how we can name a compound. Hopefully you went okay with that, and we've got a chance to test it a little bit further. So let's see if we can match these up. Hopefully you remember from the last one, we have CO. CO is carbon and then monoxide. So there we go. Okay, next one down the list, H2O. Now, we talked about this before. H2 means it's dihydrogen, and the O means monoxide. That's the proper name for water, would be dihydrogen monoxide. Third one down, CO2. Very similar to our first one, so it's going to be another carbon, but this time instead of being monoxide, it's carbon dioxide. Okay, second to last, hydrogen and sulfur. So we have 2 hydrogen, so it's dihydrogen, and we have 2 sulfur, so sulfur is going to become sulphide. And so it's dihydrogen disulphide. So that one goes here. Finally, lucky last, if you hadn't worked out, you can match it up here with sulfur hexafluoride. And the reason it's this is because we've got sulfur as our first element, fluorine is our second, fluorine becomes fluoride, and we have 6 of them, so it is hexafluoride. So there we go. Hopefully you went okay with those ones as well. Now I want to talk about some properties of covalent molecules or covalent compounds, and then we're going to move on and we're going to talk about metallic bonding and finish this video up. But first of all, our covalent molecules tend to exist, well, as gases, liquids, or solids, because they really can take any form. Okay, so they tend to have low melting temperatures, so a lot of them are actually gases, just like our non-metals often are gases as well. Generally, however, they don't conduct electricity. Now, if you remember, I was saying the reason ionic compounds are good at this is because when you put them in water, they split and they dissociate, which means the ions separate from each other, and they float around in that water as they're electrically charged ions, whether they're positive or negative. They're floating around in the water. And electricity needs charged particles that are able to move. And once those ions are doing that and they're separated, they're able to move around in that water and they're able to conduct electricity. But covalent molecules aren't able to do that. They can't conduct electricity because they don't have any free moving charged particles. This is really important for when we talk about metallic bonding, so just keep that in mind. And finally, we normally find that our covalent molecules are, well, they're insoluble in water. That means we can't dissolve them. So we can try and take them and we can try and dissolve them in water, but it's not going to happen. Think of something like oil in water and how it doesn't dissolve and it doesn't mix in nicely. It sits separate to it. That's sort of what we're talking about. Alright, so I've got a couple more diagrams down. They're just trying to reinforce that idea that in covalent bonding, the valence electrons are being shared between the two molecules, two atoms. Alrighty, and last type of bonding is metallic bonding. Metallic bonding is the really obvious one. What kind of bond would form between metals? Well, metallic bonds form between atoms of two or more metal atoms. Now, when metals bond, they do something quite different to what's happening in ionic bonds and what's happening in covalent bonds. What actually happens is those valence or those outer shell electrons, they leave. They're free to move through the lattice of positive metal ions. So if you look down the bottom left, we've got a little picture here. And you can see in purple we have what we called fixed cations. So if you remember, our metals in ionic bonds, those are the ones that are going to lose their electrons, become cations, become positively charged. And something very similar happens here. They still get rid of those electrons. They don't really want to hold on to them. So those electrons end up being free, but there's no negative ion able to take them. So those electrons just float around all free, and they float around free around these metal ions that are positive, and we call these electrons a sea of delocalized electrons. What this means is that, or rather what delocalized means, is they've been removed from their location. So delocalized means that they're no longer in their location. They've been removed from where they would normally be, and they would normally be in the valence shell of those metal atoms. So you've got all these electrons free floating around now. But there is attraction between those negative electrons and the positive metal ions, and that's actually what ends up helping hold that metal together. Metals arrange themselves, or their cations arrange themselves in what we call a lattice. So it's a really nice sort of 3D grid structure, and that's sort of how they all sit there. We've got another example on the next slide. So you can see on the right there what we're talking about sort of with a lattice. It's a 3D shape, so it goes sort of up, down, backwards and forwards and left to right. And we've got this 3D image, and you've got this very regular arrangement of metal cations with electrons all throughout it. Now, because of this, we end up with some really specific properties of metallic compounds. First of all, they can conduct electricity. Remember, electricity needs free moving charged particles, and hey, our metallic compounds have all these electrons that are floating around doing nothing, so they're free to move and that sort of thing, and they happen to have a negative charge. So that's why we use metals when we conduct electricity, because they're really good at it because of that sea of delocalized electrons. In a similar way, they're able to conduct heat because they've got particles that can move. They're also, as we were saying, ductile, and that's just got to do with how those bonds are between the atoms and how they're easily sort of remolded, or as we might say, malleable, so able to be shaped. So I'm going to talk a little bit about metals themselves and also about their reactivity. So some metals are really, really reactive. You might remember talking about the first column, our alkali metals, and even our second column, the alkali earth metals. They're really reactive metals. Contrast that with ones a bit more towards the middle of the periodic table, and you've got ones that just aren't anywhere near as reactive. And that's okay, but what it does mean is that those reactive metals can be harder to isolate because they're going to form what we call mineral ores in the ground. And mineral ores are ionic compounds. And so if you want a sample of metal that's come from that mineral ore, you actually have to go through a whole process to get it out. Now, the more easily an atom gives up those valence electrons is actually what dictates how reactive it is. So if it gives up those valence electrons really easily, it's really reactive. If it holds onto them and doesn't give them up very easily, then it's not as reactive. You can react metals with hydrochloric acid in what we call a displacement reaction. And there's an example of that down the bottom. Basically what happens is the metal kicks the hydrogen out of the hydrochloric acid and joins with the chlorine. And it's so that hydrogen gets released as hydrogen gas. And how quickly this reaction happens gives you an idea of how reactive those metals are. So for a long time, we worked with metals that were a lot less reactive because they were the ones we could find in the ground. But ancient civilizations did work out that you could take certain ores and there was a way you could actually extract metal. And this was through a process called smelting. And smelting is a process where you actually are reacting carbon with this molten ore. So you've taken your ionic compound with aluminium or whatever it is in it, you heat it up really, really hot to the point where this thing's become liquid now. It's like lava sort of thing. And you're reacting with carbon, and that's able to react and it's able to sort of purify the metal and basically end up with a pure metal coming out. So that's what ancient civilizations did, and we do similar things today to purify mineral ore and get metal samples from them. Well, when you actually combine metals, you can get something that's called an alloy. You might have heard of an alloy before. Alloys are basically, they're sort of like a new metal. They're not a new element because they're made up of 2 or more different elements, but they're a new metal that we can work with. So, like we've got there a definition, metals are formed from the combination of 2 or more different metals or a metal and another element. It doesn't always have to be another metal. The reason we do this is we might have a couple of metals and they've each got some great properties, but they might have some real problems with them as well. So the hope of creating an alloy is really that you're going to get the best of both worlds and you're going to get the best of both of their properties. So you might have one metal that's really strong but it's really brittle, and you might have another metal that's lovely and flexible but it's really weak because of that. And what you'd be hoping to do is mix them together and get something that's really strong but has enough flexibility that it doesn't shatter too easily or anything like that. And so some examples that you may not even realize are actually alloys would be, first of all, copper and tin. When you mix them together, you actually get bronze. If you take iron and carbon together, that's how you get steel. One that you probably haven't heard of is what happens when you mix gold and silver. You get something called electrum. So these are all examples where at some point someone's gone, I wonder what happens if we can make this better by mixing these 2 things together. Or maybe in the instance of iron and carbon, they've gone and done something. It's accidentally had some iron in the forge and it's reacted with some carbon and some charcoal, and they've come out with this new metal. And they're going, what is this? This is great. It's it's really strong and it's really good for this purpose. And they've ended up recreating it, and that's how we've gotten something like steel. So there's a whole different way throughout history that these sorts of things have been discovered and why they've been invented. Alright, I want to talk about something now, and this doesn't fit into necessarily into any of our types of bonding, but rather it's something that sits above them all. It's the idea of something called an allotrope. Now, you can see that the word allotrope comes from Greek, where allos means other and tropos means form. And so the word allotrope sort of means other form. And it's a word we use to talk about what happens when we get a compound, for example, carbon. We get carbon and we just have pure carbon. But when we arrange it different ways, we end up getting different compounds. For example, if we arrange it in sort of a sheet, that's what we call graphene. If we turn it into these little tubes, we might get what we call a nanotube. Example of carbon. If we arrange it into sort of a soccer ball type shape, we get what's called like a fullerene or a buckyball. And if you put it into one type of a lattice, we get a diamond. But then again, at the same time, we can sort of make lots of flat sheets in a certain manner, and that's graphite. And so this is what we're talking about. You've got diamonds and pencil lead being graphite. They're actually made from exactly the same thing, but because they're arranged differently on an atomic level and how those atoms are actually structured, we end up with very, very different compounds. So that's what an allotrope is. It's a compound that's made by arranging the same element in different ways. So it's really just different forms of the same element. Carbon's really the most common example, particularly with diamond and graphite, but it's not the only one. You can have with antimony, you've got yellow, black, yellow antimony, black antimony, or even explosive antimony. Oxygen, you could have oxygen gas, which is O2, but if you have O3, that's ozone, and there's really different properties. Iron, you might have something called ferrite, or you might get austenite, depending on how many iron atoms you've got and how you've actually got them arranged. So that's what an allotrope is. Now this brings us to the end of the Making Molecules flip chart. Hopefully you understood everything. If you didn't, please feel free to rewatch this video or to ask your teacher. Remember, when you rewatch the video, you can speed it up, slow it down, you can pause it, you can go forwards, backwards, whatever you need to get it in your head. But also remember, you can talk to your teachers if you need any more help. Anyway, thank you so much for listening to all of this.